Hello there, and welcome to the Sleepy Science Channel. Tonight we'll be drifting far across the cosmos to a time when the universe was still young, less than 1 billion years old. The first stars had only recently ignited. Galaxies were just beginning to gather. It was a time of beginnings, of slow formation, of delicate cosmic growth. And yet, one galaxy didn't wait. It appeared like a paradox wrapped in starlight, massive, luminous, busy with new stars, and impossibly old for its time. When astronomers first saw it, they assumed it had to be a mistake, a glitch in the data, a trick of the distance. Because galaxies like this weren't supposed to exist so early, not in a universe still stretching and forming. But the data kept coming, and the mystery grew. This galaxy seemed to defy the rules of galactic evolution. No cold gas, no dust, and yet it was still forming stars at a furious rate. It looked like a giant elliptical, the kind that normally takes billions of years to settle into stillness. But this one was already there, while the universe was still in its infancy. What was it doing out there? How did it grow so fast, so soon, with so little to build from? And if one galaxy like this exists, how many more are waiting to be found? Tonight, we'll follow this cosmic enigma, from its quiet discovery to the many questions it now forces us to ask. What we thought we knew may no longer be enough, and that is where the wonder begins. If you enjoy falling asleep to mysteries like these, we'd love for you to subscribe and stay with us. But for now, let's begin. It started quietly, a night like many others at the edge of the observable universe. A deep-sea eye survey designed to capture faint glimmers of ancient light. The telescope was scanning a patch of sky billions of light years away, collecting photons that had been traveling toward us since the dawn of time. Among those ancient signals, one galaxy caught the team's attention. At first, it didn't seem particularly strange, just another smudge of distant light. But as they analyzed its spectrum, something felt off. The redshift was extreme, meaning the light had been stretched across cosmic distances, placing the galaxy far back in time, over 13 billion years ago. And yet, this wasn't the faint whisper of a baby galaxy. It was loud, bright, and far too massive for its age. Galaxies in the early universe are usually small and chaotic, wisps of gas slowly coalescing into stars. But this one already seemed fully formed, as if it had leapt ahead in time. It was more like a giant elliptical, the kind of galaxy that usually takes billions of years to evolve, sitting calmly in a time when galaxies weren't supposed to exist at all. The team double-checked their measurements, then triple-checked. They looked for flaws in the data, calibration errors, anything that might explain what they were seeing. Because it couldn't be real, could it? But the signal remained clean, consistent, undeniable. They had found something that didn't belong. A galaxy that broke the timeline. A structure too large, too developed, too luminous to exist so early in the cosmic story. It would later be catalogued under a sterile identifier, just a string of numbers and coordinates. But to the astronomers who first saw it, it felt like something else. A message, a challenge, a cosmic anomaly that had no right to exist, and yet undeniably did. In the grand architecture of the universe, galaxies don't just appear fully formed. They start small, little knots of gas and dark matter gathering under gravity's pull. Over time, they grow, merge, spin, and change. The process is slow, predictable, governed by the known laws of physics and the structure of the expanding cosmos. That's why this galaxy was such a shock. It didn't fit the sequence. It didn't follow the rules. By the time a galaxy becomes massive and stable, its star formation usually winds down. It uses up its cold gas, the fuel for making new stars, and settles into quiet adulthood. The chaotic bursts of early growth give way to stillness. Spirals may become ellipticals. Colorful galaxies fade to dull red hues as their stars age. But this one was different. It was already enormous, roughly the mass of the Milky Way, and yet it was forming stars at a rate that rivaled young, messy galaxies. It wasn't fading into stillness. It was still burning with life. More confusing still, it showed almost no signs of the raw materials needed to build new stars. No rich clouds of molecular gas. No thick blankets of dust. The usual markers of galactic youth were missing, and yet the stars kept forming. It had the shape of an elliptical galaxy, which normally means it's old, quiet, and dead. But it was very much alive. The paradox was clear. This galaxy looked old, but behaved young. It looked calm, but burned hot. It was massive, but too early. Something about it, or about the physics we use to understand galaxies, wasn't adding up. Astronomers were left with two possibilities. Either something was wrong with the data, or something was wrong with our understanding of the universe. And that question, quiet, unsettling, would soon ripple through cosmology. When astronomers classify galaxies, they often begin with shape. Spirals, with their graceful arms and spinning disks, are typically younger and rich in cold gas. Ellipticals, by contrast, are older, smooth, rounded forms composed mostly of ancient stars, long past their prime. This galaxy looked like a classic elliptical. Its profile was smooth and spheroidal, lacking the clumpy structure of messy star-forming regions. There were no dusty arms, no chaotic filaments. It had the visual calm of an old red galaxy, one that had settled into a quiet retirement after a turbulent youth. But the data told a different story. Buried in the light it emitted were spectral fingerprints of young, hot stars, blue and brilliant, the unmistakable signs of recent star formation. The galaxy was still making stars, and lots of them. Somehow, it was building hundreds of solar masses worth of new stars every year. That's not supposed to happen in a galaxy like this. The visual appearance and the physical behavior were out of sync, like finding a roaring fire inside a block of ice. Ellipticals are meant to be star cemeteries, not stellar nurseries. And yet, here was a galaxy that wore the mask of age while pulsing with new life. It raised a deeper question. Could we trust what we thought we knew about structure and evolution? Was shape still a reliable sign of age and activity? Or had we stumbled onto a different kind of galaxy altogether, one born in a way we didn't yet understand? To make sense of the mystery, astronomers turned to one of their most powerful tools, stellar population analysis. By studying the light from the galaxy, they could estimate the ages of its stars, when they formed, how fast, and in what order. The results only deepened the mystery. A large portion of the stars seemed surprisingly old, some dating back to just a few 100 million years after the Big Bang. These stars had already aged considerably by the time their light reached us, which meant they must have formed incredibly early in cosmic history. But at the same time, the galaxy was still forming new stars. Bright, young, massive ones, the kind that burn hot and live fast. So now there were two conflicting signals, the presence of both ancient stars and newborn ones, overlapping in the same galaxy. This wasn't a galaxy at the beginning of its life. And it wasn't one at the end. It was both. That kind of mixed population, old stars and new stars coexisting, can happen in galaxies undergoing mergers or revivals. But those scenarios usually leave behind telltale signs, disturbed shapes, trails of dust, or bursts of violent energy. This galaxy had none of those. It was clean, quiet, undisturbed. Somehow, it had formed vast quantities of stars very early, then continued forming more across cosmic time, without ever looking messy or chaotic, like a clock that had skipped forward and backward all at once. It made astronomers wonder what kind of environment could allow a galaxy to mature so quickly, while still remaining so strangely young. And if this one had done it, could others have too? Astronomers are no strangers to false alarms. Sometimes, strange results trace back to something simple: a miscalibrated sensor, a stray reflection, a cosmic ray strike on a detector chip. So, naturally, when faced with a galaxy that defied nearly every model of galactic evolution, their first instinct wasn't to rewrite the textbooks. It was to doubt the data. Could the telescope have made a mistake? They combed through the observations, pixel by pixel, checking the instruments for signs of error. They verified the pointing accuracy, reviewed the calibration standards, and compared the data against other observations taken at different times. If a glitch had crept in, even the subtlest one, they were determined to find it. But the light was consistent. Different instruments, different wavelengths, even different telescopes, all confirmed the same thing. The galaxy was real. Its redshift placed it firmly in the early universe. Its brightness, mass, and spectral fingerprints were unmistakable. There was no artifact, no smear, no misfire in the detectors. The galaxy wasn't an illusion. And then came the confirmation from JWST. The James Webb Space Telescope, with its unparalleled infrared sensitivity, aimed its golden mirrors toward the same region of sky. What it saw matched the earlier data, but with even greater clarity. Not only was the galaxy real, it was even more luminous, even more developed than the original estimates had suggested. That was the moment when doubt gave way to awe. The mystery wasn't a fluke. It wasn't an error in the instrument. It was out there, glowing across the abyss of time. The galaxy shouldn't be there. It shouldn't look like that. It shouldn't be doing what it was doing. And yet, it was. The anomaly was now a discovery. And like all great discoveries in science, it didn't answer questions. It raised more of them. Questions not just about this one galaxy, but about how galaxies form at all. About what the early universe was truly capable of. About whether the frameworks that had guided decades of cosmology were as complete as we once believed. Something had been overlooked. Something fundamental. And the only way to find it was to start again. In the story of the universe, galaxies are among the most majestic chapters. They're not born fully written. They take shape slowly, gathering words and structure over cosmic time. It begins with dark matter, invisible halos forming the skeletons of galaxies do be. Into those gravitational wells, gas flows and cools. Stars ignite. Tiny protogalaxies merge and collide, growing larger with each interaction. Some spin themselves into graceful spirals. Others are torn into featureless blobs. Over billions of years, their personalities emerge. Young galaxies are usually clumpy and chaotic, full of hot blue stars and turbulent gas. Over time, as they burn through their star-making material, they mellow. Spirals may settle, thickening into bulges. Violent collisions can erase structure entirely, forming smooth, round ellipticals. galaxies age. They redden. Their star formation slows. Eventually, they go quiet. That's the standard narrative. It's built on thousands of observations, millions of simulations, and a deep understanding of how matter behaves under gravity. And until recently, it all seemed to hold together. From the earliest galaxies glimpsed by Hubble to the vast ellipticals we see today, the story felt cohesive, predictable. But this galaxy didn't fit anywhere in that arc. It wasn't small and chaotic, like a typical infant galaxy. And it wasn't ancient and quiescent, like an old elliptical. It had jumped the sequence, skipped ahead, become something that, according to our models, shouldn't have been possible at that stage in cosmic history. Its mere existence asked a quiet but urgent question. What if the story we've been telling is missing a chapter? Elliptical galaxies are often called red and dead. It's a phrase astronomers use with a kind of quiet finality. These galaxies are vast spherical collections of ancient stars, reddish in color, with little gas and even less activity. They've used up or lost the fuel required for star formation. No new stars are being born. No spiral arms, no nebulae, no vibrant blue clusters. Just a quiet glow from stars that formed long ago. That's how giant ellipticals are supposed to behave. They are the retirement homes of the cosmos, places where the drama of stellar birth has long since ended. Most are thought to form through the merger of spiral galaxies, violent cosmic collisions that scramble structure, expel gas, and leave behind smooth spheroidal remnants. Once the dust settles, the galaxy becomes still, quiet, passive, and they don't form quickly. Building up enough mass to become a giant elliptical should take billions of years. First, smaller galaxies have to form. Then they merge, evolve, and merge again. The process is slow, cumulative, shaped by gravity, gas, and time. So when astronomers found a galaxy in the early universe that looked just like a giant elliptical, and yet was still actively forming stars, it was like finding a fully grown redwood in the middle of a field that had only just sprouted saplings. It didn't make sense. This galaxy wasn't supposed to be here. Not yet. Not like this. And if it was, then something was off, either with the assumptions we make about how galaxies age, or with the timeline we believe the universe has followed. Because in this case, red and dead had become a lie. The galaxy was massive. It was old, but it wasn't dead at all. Every galaxy is shaped by its past, and the path it follows depends on countless factors: environment, collisions, gas supply, even its initial spin. But broadly speaking, galaxies tend to fall into two major categories. There are the spirals, flat, disc-shaped galaxies with bright arms and active star formation. These are the galaxies of motion and light. They spin like cosmic pinwheels, with dust lanes, glowing nebulae, and clusters of young stars scattered across their arms. Our own Milky Way is one of them. Spirals are vibrant, complex, and alive. Then there are the ellipticals, the opposite end of the spectrum. Spherical or oval in shape, they contain older stars, little gas, and hardly any star formation at all. Their light is redder, softer. They don't spin much, and they don't change quickly. They're the remnants of past chaos, now smoothed and quieted by time. The life paths of these galaxies diverge based on their history. Spirals can grow into ellipticals, often through mergers or interactions with other galaxies. Collisions throw off their structure, scramble their stars, and drive out their gas. Over time, a once lively spiral can become a passive elliptical. It's a kind of cosmic aging, a shift from disorder to calm. But the reverse doesn't happen. Ellipticals don't turn back into spirals. Once a galaxy has gone quiet, it stays that way. Star formation doesn't restart. Structure doesn't return. The path is one way. That's what makes this galaxy so strange. It had the shape of an elliptical, smooth, spheroidal, gas spur. But its behavior was all spiral. It was forming stars rapidly and efficiently. It was active, hot, alive, as if it had somehow chosen both paths at once. Or maybe, as if the paths themselves weren't as fixed as we thought. In the universe's grand timeline, structure builds slowly. The earliest galaxies were small, irregular, and chaotic, flickering with bursts of star formation but limited in size and complexity. Over time, those early galaxies merged, accreted matter, and evolved into the massive systems we see today. It's a process that takes billions of years, from simplicity to complexity, from turbulence to structure. But this galaxy didn't seem to care about any of that. It looked like it had skipped ahead, as if someone had fast-forwarded its evolution. It wasn't a faint smudge of infant light. It was fully formed, massive, smooth, and stable. The kind of structure we'd expect to find many billions of years later, not in a universe barely 700 million years old. To put that in perspective, imagine a baby born in the morning and walking into a college classroom by nightfall. That's how out of place this galaxy felt. Its mass alone was staggering. Galaxies of this size take time to grow, time to gather gas, time to form stars, time to merge with neighbors and build up the gravitational heft we associate with maturity. But this one had already done all of that, somehow, in a fraction of the time. And the strangest part, it wasn't slowing down. It was still forming stars, not just a few here and there, but in massive bursts, on par with the most active galaxies known. It had all the signs of a galaxy still in the throes of growth, while already wearing the shell of something ancient. It challenged more than just our models. It challenged our sense of cosmic time. Because if galaxies like this could form so fast, so early, then maybe our picture of the universe's childhood, this quiet, slow period of building, was wrong. Maybe the early cosmos wasn't so quiet after all. Galaxies like the Milky Way are thought to have formed gradually. They started small, merging with other galaxies, accumulating gas, forming stars over billions of years. Even now, the Milky Way is still growing, still pulling in matter, still evolving. That slow, layered process is a key feature of how we understand galactic development. But this galaxy was different. It already had as much mass as the Milky Way, maybe more. And yet, it existed in a universe less than 1 billion years old. That's a blink of an eye in cosmic terms. There simply shouldn't have been enough time to gather that much material, to form that many stars, to become so large and structured. And despite all that mass, it didn't act old. Its star formation rate was extraordinary, hundreds of times higher than the Milky Way's today. Its core was blazing with new stars, all packed into a compact region. There was no sign that it was winding down, no indication that it had reached maturity and settled. If anything, it was still in its growth phase, still surging forward. It was like finding a mountain already carved by glaciers before the planet had even cooled. That combination, mass and activity, made it a true anomaly. Not just in one category, but across the board. It had grown too fast, formed too soon, and continued burning far too brightly for its age. And the more astronomers examined it, the more they began to wonder if it was part of a larger pattern. Because what if this wasn't just a one-off event? What if this galaxy wasn't alone? Astronomers gave it names, catalogue numbers, classifications. They labeled it as a compact, quiescent galaxy with anomalous star-forming traits. They placed it into spectral bins and mass ranges. They tried, with every tool at their disposal, to slot it into the familiar taxonomy of the cosmos. But the truth was, it didn't belong in any category. It didn't behave like a spiral or an elliptical. It wasn't a merger remnant. It wasn't a dusty starburst galaxy. And it wasn't the slow-growing early object predicted by our simulations. It was something else, something that seemed to blur the boundaries between youth and age, between growth and stillness. It existed in a kind of in-between state, massive but not quiet, active but not chaotic. It had somehow achieved both stability and vigor, both calm and combustion. It looked like a galaxy that had completed its story, but it was still writing new chapters. And the more scientists tried to explain it, the more it slipped through their definitions. It didn't show signs of a recent collision. It wasn't gathering gas from outside. It didn't have the irregularities or scars you'd expect from rapid, violent growth. Everything about it was smooth, composed, balanced. It shouldn't have had any fuel left, but it did. It shouldn't have formed so fast, but it had. It shouldn't still be forming stars, but it was. There was no law that outright forbade such a galaxy from existing. But all the probabilities leaned against it. It would have required a perfect sequence of events, a precisely tuned set of conditions, all happening at breakneck speed in a very young universe. And yet, it was real. It was measurable. It was right there. So then came the bigger question. If one galaxy like this could form so early, what if it wasn't unique? What if it wasn't a freak event, but the first hint of a pattern we'd been blind to? Because if the universe could produce even one structure like this, it might have produced many. At first, no one expected to find more. The discovery was seen as a cosmic fluke, an edge case that would be remembered mostly for what it challenged, not what it implied. Scientists assumed it would remain alone. Mysterious, yes, but singular. But then came the follow-ups. New instruments scanned other deep fields, looking farther and deeper into the early universe than ever before. And there, hiding in the noise, were more smudges of light. Some faint, some blazing, some eerily similar to the original. One by one, galaxies began to emerge from the background, all sharing the same strange profile. Massive, bright, old, and yet active. Galaxies that had no business being so well formed so early. Galaxies that seemed to have sprinted through the usual steps of cosmic evolution and arrived at a destination they shouldn't have reached for billions of years. As the list grew, it became harder to explain them away. They weren't just one-off events. They weren't observational errors. They were everywhere, not common, but not rare either. Present in every deep field survey, lurking in datasets from Hubble, from ARMA, from the Spitzer Space Telescope. And when JWST opened its eyes, the mystery only deepened. It became clear that this was more than a curiosity. It was a population, a class of galaxies that had been largely invisible to us until now, hiding in the earliest epochs of time, carrying stories we had never thought to imagine. The galaxy that started it all was no longer an anomaly. It was a clue. The search intensified. Astronomers began combing through archival data, reanalyzing old surveys with new eyes. What had once seemed like background noise or statistical outliers were now potential candidates. And as the filters were refined, as the search criteria adjusted to look for galaxies that were too big, too early, too bright, more and more began to emerge. 1 turned into 5. 5 turned into 20. Some were brighter than the original. Others were even more compact. A few showed signs of extreme starburst activity, forming stars 1,000 times faster than the Milky Way. And nearly all of them existed within the first billion years after the Big Bang. They were scattered across the sky, each one sitting quietly at the edge of visibility, waiting to be noticed. Most galaxies from this early epoch are faint and wispy. They resemble seedlings just beginning to sprout. But these were fully grown trees, massive, structured, mature. They had all the hallmarks of systems that should have taken billions of years to assemble. Yet they had appeared almost immediately, as though the universe had skipped its own instructions. And the numbers didn't lie. These galaxies were not isolated anomalies. They were statistically significant. Too many to ignore. Too consistent to dismiss. Each one chipped away at the certainty of our models, revealing cracks in the foundation of how we thought the cosmos builds its stars and structures. It wasn't just that one galaxy didn't make sense. It was that dozens didn't. And they were all telling the same story. Something in the early universe was more efficient, more aggressive, more capable than we had ever imagined. And soon, a new question began to take hold, not just among theorists, but among cosmologists everywhere. Were these galaxies breaking the rules, or had we never really understood the rules to begin with? When the James Webb Space Telescope launched, scientists hoped it would sharpen the picture of the early universe to give clarity to our models, refine our timelines, and fill in the gaps of how galaxies form and grow. What it did instead was set everything on fire. Within months of its first deep field observations, JWST confirmed what previous telescopes had only hinted at. The universe was teeming with massive, mature galaxies far earlier than any model bar had predicted. What Hubble could only suggest, Webb could now see in exquisite detail. These galaxies weren't just real, they were everywhere. JWST found them lurking in the earliest slices of cosmic time, just a few 100 million years after the Big Bang. Some had masses rivaling or exceeding that of the Milky Way. Some were forming stars at staggering rates. Others appeared to have exhausted their star-making gas entirely, already entering quiet, post-starburst phases long before the universe was expected to allow it. And it wasn't just the number of galaxies that surprised astronomers. It was their properties, their structure, their light, their chemistry. Many showed signs of heavy elements, carbon, oxygen, iron, elements forged in the cores of stars and spread by supernova. But that enrichment takes time. Generations of stars must live and die to create those elements. So how, in a universe less than 1 billion years old, were we already seeing galaxies enriched with metals? It meant these galaxies had not only formed stars quickly, they had lived through entire stellar life cycles, formed, burned, exploded, and enriched. All in record time. JWST, with its unmatched sensitivity to infrared light, peeled back the veil of cosmic history. And what it revealed was not a peaceful dawn, but a universe already ablaze with complexity. Our models, it seemed, had underestimated the universe's ambition. It hadn't tiptoed into complexity. It had sprinted. And suddenly, the impossible galaxy was no longer alone. It was the first voice in a growing chorus. A signal, echoing from the beginning of time, that we had missed something fundamental. Some of the galaxies discovered by JWST weren't just massive or mature. They were explosive. Their star formation rates were so high, they seemed to break the limit set by physics itself. Hundreds, sometimes thousands of stars forming each year, an astronomical frenzy happening inside structures only a fraction the size of modern galaxies. In the nearby universe, galaxies that form stars this quickly are rare, unstable, and usually triggered by dramatic collisions. They burn through their gas in a flash and often collapse into quiescence soon after. But these early galaxies, these ancient giants, were forming stars faster than almost anything seen today, and they were doing it with eerie calm. No evidence of recent mergers, no signs of chaos, just a smooth, compact galaxy forming stars at an impossible rate. To produce that many stars, a galaxy needs fuel, cold hydrogen gas that can collapse into dense molecular clouds. But the early universe was still hot, still settling. Gas wasn't supposed to cool and condense so quickly. Yet somehow, these galaxies had found a way to leap ahead, to gather and compress their fuel at breathtaking speeds. It raised an uncomfortable possibility. Either the conditions in the early universe were far more conducive to star formation than we thought, or our entire understanding of how gas cools, collapses, and ignites incomplete. There are physical limits to how fast a galaxy can turn gas into stars without tearing itself apart. Radiation pressure, supernova feedback, gravitational instability. These mechanisms act as natural brakes, slowing the process, regulating the pace. But these galaxies didn't seem to care. They formed stars faster than the models allowed, without blowing themselves apart. No braking, no slowing, just relentless, sustained creation. It was as if the universe, in its youth, had more energy, more freedom, or simply more creativity than we ever gave it credit for. And if galaxies could grow this fast, then how early could the biggest ones have begun? The age of the universe is not just a number, it's a constraint. A boundary that tells us what should be possible and when. When the first stars could have formed. When the first galaxies could have assembled. When the elements we depend on, carbon, oxygen, iron, could have emerged from the hearts of dying stars. Everything in cosmology is built on this timeline. A progression from simplicity to complexity, mapped across billions of years. But these galaxies were challenging that framework at every level. Some of them, seen just 300 or 400 million years after the Big Bang, already contained more mass than entire galactic clusters. Others showed signs of chemical enrichment, heavy elements forged in multiple stellar generations. Some were no longer forming stars at all. They had already peaked, already quenched, already begun to fade. In a universe that young, this should have been impossible. To reach that point, a galaxy would have needed to collapse from gas, form its first stars, undergo cycles of supernova, cool again, and ignite new waves of formation, all before the cosmic clock had even ticked past its first billion years. It was like discovering an ancient ruin buried beneath a city that hadn't been built yet. Worse still, some of the galaxies didn't just challenge our models, they mocked them. Simulations built on the CDM framework, the standard model of cosmology, couldn't produce galaxies this massive, this early, even when pushed to extremes. The inputs could be tweaked, the parameters adjusted, but the results always came up short. The galaxies we were seeing in the sky weren't in the simulations. And the deeper we looked, the more it felt like we weren't just dealing with edge cases. These galaxies weren't flukes. They were frequent, numerous, predictable in their unpredictability. We weren't just looking at a few broken rules. We were looking at a broken timeline, one that had quietly unraveled beneath our theories. one that had allowed entire galactic empires to rise and burn long before we ever imagined it was possible. The alarm bells were no longer faint. With each new observation, with each new early universe galaxy that defied expectations, the quiet questions began turning into loud systemic doubt. Were our models of galaxy formation broken? For decades, simulations of the universe's evolution had followed a clear narrative. Matter formed into dark matter halos. Gas fell inward, cooled, collapsed, formed stars. Small structures merged to become larger ones. Galaxies slowly assembled, regulated by gravity, feedback, and the expanding fabric of space itself. It was elegant, predictable, and it worked, at least, within the limits of what we could see. But those limits had changed. JWST had extended our reach deeper into the past than ever before. And what it revealed was a universe far more advanced, far more structured, and far more ambitious than anything the models predicted. It wasn't just one aspect that failed. It was everything. The mass of galaxies, their chemical makeup, their star formation rates, even their morphology. In every measurable category, the simulations underestimated what the early cosmos was capable of. Some theorists tried to save the models by pushing them harder, by increasing the density of primordial gas, by accelerating star formation efficiencies, by tweaking the rates of cooling, collapse, and feedback. But the more they tweaked, the more artificial the results became. Others began to whisper what no one wanted to say out loud, that perhaps the simulations were wrong because the assumptions behind them were incomplete. Maybe dark matter doesn't behave quite the way we think. Maybe the early universe had phases we've never accounted for. Maybe the cosmic conditions shortly after the Big Bang were stranger, more fertile, more unstable than any of our equations suggest. Because these galaxies were real. They weren't mistakes or illusions. They were fully formed islands of matter and light, already racing ahead at a time when the universe was still learning to walk. And if reality diverged this sharply from theory, then maybe it was time to let go of the theory. From the very beginning, cosmologists have described the universe as a story that unfolds in chapters. The earliest chapters are slow, quiet. Particles form. Atoms cool. Gravity gathers matter. Tiny fluctuations in the cosmic microwave background become the seeds of galaxies. And over hundreds of millions of years, the first stars begin to shine. That was always the model, a universe that builds slowly. First, small galaxies, irregular, chaotic, clumpy. Then, over time, mergers and growth, gradual accumulation of mass, the cooling of gas, the recycling of stellar material, a long, drawn-out process that eventually gives rise to the vast luminous galaxies we see nearby. But the discoveries now pouring in from deep space telescopes suggest a different story, one in which complexity appears almost immediately, one in which the cosmic dark ages weren't so dark or so quiet after all, a story in which galaxies didn't wait patiently to grow. They exploded into being, already massive, already active, already filled with stars. The slow-building timeline, once thought unshakable, is now riddled with exceptions. And those exceptions are beginning to outnumber the rules. It's as if the universe skipped its prologue, as if the earliest chapters of the story were more densely packed, more explosive, more accelerated than anyone expected. And if that's true, then we may have to rewrite the opening lines of cosmic history entirely. The universe was still in its infancy. When light from these galaxies began its journey, space itself had only just settled from the violent expansion of the Big Bang. Temperatures were still high. The first stars had only recently formed. Black holes were still newborn. The cosmic web, that vast network of filaments and voids, had barely begun to take shape. This was supposed to be a quiet time, a formative time, a moment in cosmic history when galaxies, if they existed at all, would be small, irregular, and primitive, like seedlings just beginning to rise from the soil. But these galaxies didn't look like seedlings. They looked like forests, already mature, already massive, already ablaze with light. They weren't disorganized clumps of gas and dust. They had structure. They had chemistry. They had entire populations of stars, some of them already old by cosmic standards. They weren't merely forming, they had already formed. It's as if someone had turned the clock forward too far. As if we'd glimpsed into a much older universe than the timeline allowed. But the redshift data was clear. These galaxies existed when the universe was only a few 100 million years old, not billions. It was like finding a child with the memories of an adult, a mind that had lived more than its years could possibly hold. And it begged a deeper question. Was this anomaly a rare event, or had we fundamentally misunderstood how quickly the early universe could grow? Because if galaxies could reach maturity while the cosmos was still taking its first breaths, then our sense of cosmic age, of what's early and what's late, might need to be completely redefined. There's a kind of gravity to mass. Not just the physical kind, but a conceptual one. The more massive an object is, the more it commands attention, the more questions it raises about how it came to be. And the galaxies JWST found in the early universe were shockingly massive. Some had stellar masses equal to or greater than the Milky Way. Others approached the scale of the largest galaxies we know, elliptical giants that normally take billions of years and dozens of mergers to assemble. But these weren't ancient relics. They existed when the universe was less than 5% of its current age. To accumulate that much mass so early defied every known mechanism. There simply hadn't been enough time. Not enough cold gas. Not enough collapsed halos. Not enough anything. Galaxies grow by merging, by pulling in smaller neighbors, by gathering gas from the cosmic web, by building themselves slowly through countless interactions. But mergers take time. Gravity works on slow, deliberate scales. And gas cooling, star formation, and feedback all come with their own delays and inefficiencies. So, how did these galaxies leap ahead? One possibility is that they formed in extremely dense regions, cosmic overdensities where gas pooled more quickly and gravity worked more efficiently. Another is that the first stars, massive and short-lived, seeded rapid enrichment and collapse. Or perhaps the early dark matter halos were more effective at drawing material inward than we had realized. But none of these explanations quite added up. Even under the most favorable conditions, simulations struggled to produce galaxies of such mass so early. The physics just wouldn't allow it, not without making 1,000 other predictions that don't match the universe we observe. It left scientists with a troubling realization. If the mass is real, and all evidence suggests it is, then we're missing something big. Because a galaxy this massive, this fast, this soon, doesn't just bend the rules, it rewrites them. For galaxies to form, raw material is essential. Hydrogen, helium, the basic building blocks that collapse under gravity, ignite into stars, and spin into structure. In the early universe, those materials were abundant, but they were also hot, diffuse, and chaotic. According to our models, it should have taken hundreds of millions of years for that primordial gas to cool, settle, and condense into star-forming clouds. But maybe we underestimated it. maybe the gas in the young universe wasn't as sluggish or as inefficient as we thought. Maybe, under the right conditions, it could cool faster, collapse harder, and form stars more explosively than any simulation has yet managed to show. There are mechanisms that might help explain it. For example, early gas clouds may have had higher densities than expected, or interacted with surrounding radiation fields in unusual ways. Cooling through atomic hydrogen and helium could have happened more efficiently in dense, metal-poor environments. And turbulence, usually thought to slow collapse, may in fact have driven it faster in some conditions. Or perhaps the role of dark matter has been misunderstood. If early dark matter halos were more clumpy or more aggressive in pulling gas inward, that could have jump-started galaxy formation earlier than predicted. There's also the idea that some of the first stars, known as population the third stars, were truly massive, burning quickly and violently, enriching the surrounding gas in record time. If even a few of these stars exploded near dense gas clouds, they could have seeded the conditions for rapid starburst events almost immediately. But even these ideas only go so far. None of them, alone, can account for the sheer mass, speed, and structure we're seeing. They help around the edges. They soften the contradiction. But they don't resolve it. To do that, we may need to rethink not just how galaxies form, but how the early universe itself behaved. Because maybe the story isn't just about guess. Maybe the Big Bang gave rise to more than we expected. The Big Bang is often described as a singular, clean event, an expansion of space and time that gradually cooled, slowly forming particles, atoms, stars, and galaxies. But in truth, it may have been messier, wilder, more fertile than we ever imagined. What if the earliest moments of the universe were not just fast, but violently creative? Some theorists have begun to ask whether the aftermath of the Big Bang could have produced conditions far more conducive to rapid galaxy formation than our models account for. Not just through temperature and density, but through deeper physical mechanisms, ones tied to the fabric of space itself. One idea involves phase transitions, cosmic shifts in the underlying forces of nature that occurred as the universe cooled. Just as water turns to ice, the early universe may have passed through transitions in its fundamental fields. These transitions could have generated massive fluctuations in density, pockets of gas and energy that seeded galaxy formation at scales far earlier than we expected. Another possibility is that the inflationary period, the rapid expansion that occurred in the first fractions of a second, left behind variations more extreme than we've detected so far. In certain regions, space may have stretched less, creating zones of higher density where galaxies could form faster and earlier. And then there's the potential role of primordial black holes, hypothetical remnants from the earliest instants after the Big Bang. If they existed, even in small numbers, they could have acted as seeds for galaxy formation, anchoring dense clouds of gas and pulling in matter long before the first stars lit up. All of this points to a deeper truth. We don't fully understand the conditions that existed in those first few 100 million years. We've extrapolated, we've simulated, but we'd never seen them, not until now. And what we are beginning to see is a universe that may have erupted into complexity far more violently, far more quickly, and far more richly than we dared to imagine. Not a gentle unfolding of structure, but a cosmic storm, birthing galaxies almost as soon as the universe could hold them. The contradiction was becoming impossible to ignore. Everywhere astronomers looked in the early universe, they began finding galaxies that didn't match their surroundings. Not just massive or luminous, but strangely mature, as if they had lived through entire epochs of development before the universe was even a billion years old. They weren't supposed to be there. At that time, the cosmos was still young. Background radiation was still warm. The first galaxies were expected to be clumpy and chaotic, simple beginnings to what would become vast spirals and ellipticals over time. But these galaxies weren't beginning. They were already far along. Some had old stars. Others had well-defined structure. Many showed signs of enrichment, evidence that multiple generations of stars had already lived and died. A few had already shut down star formation entirely, entering quiescence long before such behavior was thought possible. It was like seeing a forest in full autumn color during the first days of spring. How could they evolve so quickly? How could they reach this state in just a few 100 million years? Even the speed of light, the ultimate limit of the universe, couldn't make sense of it. The math didn't work. But timelines didn't line up. And it wasn't just one or two examples. It was a population. A whole class of galaxies that had quietly matured in the background of the early cosmos, only now coming into view with our most powerful telescopes. This wasn't a simple calibration error. It wasn't a matter of missing dust or mismeasuring redshifts. The more the data was checked and cross-checked, the clearer the conclusion became. We're seeing mature galaxies in a baby universe. And that means one of two things must be true. Either our understanding of how galaxies form is incomplete, or our understanding of time itself, of cosmic chronology, is due for revision. Because something in the early universe was moving much faster than it should have. Much, much faster. When scientists are faced with unexplained mass in the early universe, one of the first ideas they consider is black holes. Not the stellar kind, not the remnants of dying stars, but bigger ones. Supermassive black holes, the kind that live at the centers of galaxies, anchoring entire systems with their gravitational pull. These monsters weigh millions or even billions of times more than the Sun, and they shape the evolution of galaxies around them. What if these ancient galaxies formed around black holes that came first? It's a reversal of the usual order. Normally, stars form, then galaxies assemble, and black holes grow in the center. But maybe, just maybe, some of the earliest black holes formed before the galaxies. Maybe they were born from the collapse of massive gas clouds or through exotic physics tied to the very early universe. If a black hole formed with enough mass and fast enough, it could have acted like a seed, drawing gas, dark matter, and debris inward, building up a galaxy in record time. Gravity works quickly when the conditions are right. And in a dense, hot, rapidly expanding universe, those conditions might have been more common than we realized. There's even speculation that some of these black holes might have formed directly from collapsing regions in the early cosmic web, bypassing stars altogether. These are known as direct collapse black holes. If they existed, they could have created enormous gravitational wells, pulling material together at rates that would be impossible under normal circumstances. But there's a catch. Even this theory has limits. The numbers are tight. The timeline is short. And while early black holes might explain the core of these galaxies, they don't fully explain the smoothness, the star formation rates, or the diversity of structures we're seeing. Still, it's one of the most compelling ideas on the table. Because if the universe planted black holes first, then maybe everything else grew up around them. Dark matter is the invisible scaffolding of the cosmos. Though we can't see it directly, we know it's there, pulling galaxies into shape, guiding the formation of clusters, threading the universe with its silent gravitational presence. Galaxies form where dark matter clumps. Where it gathers, gas follows. And where gas settles, stars are born. But what if we missed something? Our simulations rely on estimates of how dark matter behaves. They assume smooth distributions, gradual accumulation, a certain rhythm to the growth of structure. But what if the early universe wasn't so smooth? What if dark matter clumped faster, or collapsed harder, or behaved in a way that allowed galaxies to form earlier than expected? It's possible that some of the first dark matter halos, the gravitational wells that would become galaxies, formed not just sooner, but in far greater numbers or densities than our models have allowed. If those halos were more massive or more concentrated, they could have drawn in gas more rapidly, triggering the formation of stars far earlier than we thought possible. There's even a chance we've been overlooking certain kinds of small-scale structure, tiny dark matter knots that didn't survive into the present day, but played a crucial role in the early acceleration of galactic growth. These primordial clumps may have acted like sparks in dry kindling, lighting the fires of star formation in places we never expected to burn so hot, so fast. And because dark matter doesn't emit or reflect light, these structures would be effectively invisible to us, ghosts that shaped the visible universe without ever leaving a trace we could directly observe. If we've underestimated the role of dark matter, if it worked differently, or formed faster, or left behind patterns we've missed, then much of what we believe about galaxy formation might need to be revised. Because maybe it's not the galaxies that are unusual. Maybe it's our map of the invisible that needs to change. Simulations have been our guides through cosmic history. They take in the laws of physics, the observed properties of matter, the expansion of the universe, and from those ingredients, they try to recreate how galaxies form, evolve, and cluster over billions of years. Some are vast and detailed, requiring supercomputers to run for weeks. Others are streamlined, optimized for speed, designed to test a narrow set of conditions. But no matter how sophisticated the simulation, it is still a simplification. The real universe is messy, full of chaos and feedback and cascading interactions that don't always scale in neat, predictable ways. Star formation isn't just about cooling gas. It's shaped by magnetic fields, turbulence, shock waves, and the energy output of stars and supernova. And those effects aren't always captured in full detail. So when JWST began revealing galaxies that didn't fit the simulated timelines, the question wasn't just what's wrong with the universe. It was, what are we missing in the models? Many simulations assume a kind of order, an average pace of growth, a standard sequence of events. But maybe the universe doesn't favor averages. Maybe it thrives on extremes. Maybe the earliest galaxies formed in environments so dense and energetic that they tore past the normal constraints, assembling in ways we never anticipated. Our models are built to match the galaxies we see nearby, systems that have had billions of years to settle and evolve. But the early universe wasn't settled. It was wild, hot, full of collisions and streams of gas and untamed fluctuations. Simulating that kind of chaos is hard. Even the best models use approximations for what happens at small scales, in star-forming clouds, in supernova explosions, in the tangled flows of intergalactic gas. Those approximations work well most of the time. But the galaxies JWST is finding may be the exceptions, products of rare, intense conditions that our simulations don't yet know how to handle. It doesn't mean the simulations are useless. Far from it. They've helped us understand how structure forms, how galaxies cluster, how stars evolve. But they are not the universe itself. They're just stories we've written based on the physics we know. And sometimes, when the real story unfolds, we realize we've left entire chapters blank. Star formation seems like one of the better understood processes in astronomy. Gas cools, collapses under gravity, and fragments into dense clumps that ignite into stars. We've observed this in nearby galaxies, modeled it in labs, and watched it unfold in the cloudy nurseries of our own Milky Way. But all of that understanding is based on today's universe. Cool, structured, relatively stable. The early universe was none of those things. It was hotter, denser, more chaotic. Radiation fields were stronger, magnetic turbulence more extreme. Gas was more pristine, lacking the heavy elements that help it cool and collapse in the modern era. What if, in that environment, star formation played by different rules? Some researchers now wonder whether the early universe had its own unique modes of star formation, ones that allowed gas to collapse more efficiently or fragment less, leading to the creation of massive stars at breakneck speed. Without dust or metals to regulate temperature, the gas clouds may have behaved differently, faster, more violently, less constrained by the feedback loops that today tend to slow the process down. These differences could explain how galaxies in the early cosmos formed stars so rapidly and with such surprising efficiency. It's also possible that the very first generations of stars, those so-called population, the third stars, had qualities unlike anything we see today. Enormous, hot, short-lived. Their lifespans measured in millions of years, not billions. They may have formed in bursts, supercharging the environment around them, triggering waves of collapse that gave rise to the next generation almost instantly. In a universe only a few 100 million years old, even tiny changes to how gas behaves, how easily it cools, how it responds to gravity, could have massive consequences. So maybe it's not the timeline that's broken. Maybe it's the physics, or rather, the assumption that the physics of now must apply to then. We think we know the history of the cosmos, from the hot flash of the Big Bang to the cooling glow of recombination, to the long, dark ages before the first light appeared. We've traced it all with incredible precision. Radiation maps, spectral fingerprints, redshift surveys. Everything seems to tell the same story. But what if we're reading the story out of order? Some of the galaxies JWST has uncovered seem to violate the expected timeline of cosmic evolution. They show signs of maturity long before the universe should have allowed it. They exist at redshifts that place them firmly in the earliest chapters of cosmic time, and yet they behave like galaxies that should have taken billions of years to grow. It's led some theorists to ask an unsettling question. Could we be wrong about when things happened? The idea isn't that the Big Bang occurred at a different time, but that our interpretation of distance, light travel time, and expansion could be flawed in subtle ways. We calculate the age of the universe based on how far light has traveled, how stretched its wavelengths have become over time. But if there are unknown factors at play, if the rate of expansion changed in unexpected ways, or if the geometry of space-time itself is more complex than we assume, then our age estimates could be off. Alternatively, we might be misinterpreting what these early galaxies are. Some may not be as old or massive as they appear. Others might be gravitationally lensed, magnified by foreground matter, tricking us into seeing something bigger or brighter than it really is. But so far, the lensing explanations haven't held up, and the spectral data keeps coming back with the same message. These galaxies aren't illusions. They are old. They are massive. They are real. And if that's true, then maybe the problem isn't in our telescopes. Maybe it's in our assumptions. Because even the most careful timeline can unravel if the clock it's built on is slightly, quietly wrong. Every explanation so far has helped, a little. Some suggest that dark matter collapsed earlier than expected. Others propose new modes of star formation, or primordial black holes acting as seeds for galactic growth. Some theories invoke exotic physics from the early universe, tweaks to inflation, adjustments to the cosmic expansion rate, or alternate interpretations of redshift. Each idea patches one piece of the puzzle, but none of them explain it all. They can't account for the sheer number of early massive galaxies, or for their unexpectedly smooth structures, or their strange mixture of young stars and old stellar populations, or the heavy element abundances that shouldn't exist yet, or the galaxies that have already stopped forming stars by the time the universe is just a few 100 million years old. Every theory comes with a catch, a consequence that breaks something else we know. And that's the problem. In science, the best explanations aren't just creative, they're consistent. They make new predictions. They explain the anomaly and fit with everything else we observe. But when it comes to these galaxies, every proposed fix causes another thread to unravel. The more data we collect, the clearer the mismatch becomes. The models aren't just off by a little. They're off by orders of magnitude. The timelines are off. The star formation rates are off. The masses are off. And every adjustment, every new parameter or patch, begins to feel more like a workaround than a solution. It's not that we've failed to explain one galaxy. It's that we may have fundamentally misunderstood how the early universe works. And that realization is both terrifying and thrilling. Because if none of our explanations are quite right, then maybe the answer isn't just around the corner. Maybe it lies somewhere deeper, somewhere we haven't looked. We often talk about the laws of physics as if they are eternal, unchanging, fixed across time and space. Gravity behaves the same today as it did billions of years ago. Light travels at the same speed. The fundamental constants, Planck's constant, the gravitational constant, the charge of the electron, are presumed to be universal truths. But what if they're not? Some theories in physics allow for the possibility that these so-called constants aren't actually constant. That in the earliest moments of the universe, the rules may have been more fluid, not broken, but evolving, sharpening into focus as the cosmos cooled and expanded. If the strength of gravity were even slightly different, galaxies could collapse faster or slower. If the fine structure constant, which governs how light and matter interact, were altered, it could change how stars form and how radiation moves through gas. Tiny differences in the rules could lead to dramatic differences in outcomes. In other words, the early universe might not have played by the same rules we observe today. There's also the idea of varying speed of light theories, models in which light traveled faster in the early universe. This could compress timelines, allowing structures to form more quickly than they otherwise could. Or perhaps the vacuum of space itself had different properties, influencing how energy condensed into matter. These aren't mainstream ideas, and they come with challenges of their own. But the fact that scientists are even considering them speaks to the scale of the mystery. When faced with galaxies that shouldn't exist, we're forced to question the deepest assumptions, even those that have held for decades. Because if the laws of physics were still settling, if the universe was still learning how to behave, then perhaps the early cosmos wasn't just younger. It was wilder. Speed is a funny thing in cosmology. Not just in the sense of motion, but in the rhythm of change, how quickly matter collapses, how fast structures assemble, how rapidly complexity emerges. Our models assume a steady tempo, a cosmic pace, one dictated by the laws of physics and the cooling expansion of space. But some theories suggest that in the earliest moments, everything may have moved faster. Not metaphorically, literally. In the early universe, fast physics view, the constants that govern structure, the rate at which gas cools, the strength of interactions between particles, even the speed of light itself, may have been different in those first hundreds of millions of years. Not wildly different, but just enough to accelerate how quickly matter could organize itself into stars and galaxies. Even a small boost in the rate of cooling could mean the difference between galaxies forming in a billion years or in a few hundred million. Some of these ideas come from attempts to solve other problems in cosmology, like the horizon problem or the flatness problem, and suggest that during or just after inflation, the physics of the universe briefly entered a kind of hyper-efficient state. A universe that was not just dense and hot, but astonishingly productive. Faster cooling, faster fusion, faster collapse. That doesn't mean galaxies popped into existence overnight, but it could mean that processes we thought required long spans of time, star formation, metal enrichment, the settling of galaxies into structure, all happened on a compressed scale. And if that's the case, then these early galaxies aren't violating the rules. They're revealing them. Because maybe the universe didn't start slow. Maybe it rushed into being with an urgency we're only now beginning to glimpse. Time, in a sense, might have flowed differently at the beginning. Not because the clock ticked faster, but because everything else did. There's another possibility, stranger, more speculative, but haunting in its implications. What if these galaxies didn't belong to this cycle of the universe at all? Some cosmologists believe the Big Bang wasn't the absolute beginning, but a transition, the latest in a long series of cosmic cycles. Expansion, contraction, bounce, repeat. If the universe has existed through multiple iterations, each one giving birth to the next, then perhaps traces of those earlier epochs could remain. In this view, the early universe we see isn't the very beginning. It's the continuation of a story already in progress. And maybe, just maybe, some structures from that previous universe survived the transition. Not intact, like islands floating across time, but embedded in the fabric of the new cosmos. Patterns in the density field, residual fluctuations, or even whole regions that carried forward condensed matter, compressed energy, seeds of galaxies too early and too advanced for this round of cosmic evolution. It's speculative, wild, difficult to test. But when you observe galaxies that seem older than the universe around them, that carry more mass, more history, more complexity than the current timeline allows, the idea doesn't seem quite as distant as it once did. Because if our universe has cycled before, if it has burned and rebirthed itself in an eternal rhythm, then perhaps what we're seeing isn't a mistake. Perhaps we're glimpsing the memory of another cosmos, written in the starlight of galaxies that shouldn't exist, but somehow, quietly, do. At the smallest scales, space and time begin to blur. Quantum gravity is the name we give to the unknown, the uncharted frontier where the rules of general relativity and quantum mechanics collide. We don't yet have a complete theory, but we know this. In the earliest instance after the Big Bang, quantum gravity must have mattered. And if it mattered then, maybe it left behind fingerprints. Some researchers wonder whether quantum effects could have influenced the formation of structure in ways we're only beginning to understand. Tiny fluctuations in energy density, driven by quantum uncertainty, might have been amplified by inflation, seeding galaxies not randomly, but with patterns and symmetries we don't yet recognize. Or perhaps quantum gravity affected the geometry of space itself, warping distances, altering collapse rates, shifting the thresholds for when gas becomes dense enough to ignite into stars. There are even ideas from loop quantum gravity and string theory suggesting that in the earliest epochs, space-time wasn't smooth but granular, made of tiny loops or vibrating strings that behaved differently under Saphir. Extreme energy conditions. In such a universe, gravity could have acted more strongly at small scales, encouraging matter to clump faster than classical physics predicts. These aren't just mathematical curiosities. They're testable ideas, barely, at the edge of what our instruments can measure. but the strange galaxies we're now observing may offer rare clues. Their existence may reflect conditions where quantum gravity played a direct role in how matter organized. What we see in them, their density, their mass, their speed, may not just be the result of gas and stars and time. It may be the residue of physics from a deeper layer of reality, a glimpse into the scaffolding beneath space-time. And if that's true, then these galaxies aren't just early. They are ancient in a different way, born not just of matter, but of the laws that gave rise to everything. As telescopes reach farther and clearer into space, a new picture is emerging, one that challenges the neat categories we once used to define galaxies. We used to think of them as relatively simple, spirals or ellipticals, active or passive, young or old. We had models that sorted them by color, shape, star formation rate, metallicity, environment. And for a long time, that was enough. But now, we're beginning to see galaxies that don't fit any of those molds. Some are ultra-compact, galaxies packed tightly with stars, smaller than a tenth the size of the Milky Way, but with just as much mass. Others are diffuse and ghost-like, enormous in size, but so sparsely populated with stars that they appear as faint smudges drifting between galaxy clusters. There are galaxies with no dark matter, galaxies with almost no stars, galaxies with supermassive black holes but little else, galaxies shaped like rings or lenses or irregular knots of light. And the more we look, the stranger they become. In the early universe especially, we're finding systems that seem to bend every rule. Galaxies that formed too fast, aged too early, or burned too brightly to make sense. Each new deep field image reveals more of them, each one an outlier that pushes the boundaries of our understanding. But maybe they're not outliers at all. Maybe the universe isn't built on a few dominant galaxy types with occasional exceptions. Maybe it's built on diversity, rich, chaotic, unpredictable diversity. A cosmic jungle, not a manicured garden. One in which the standard galaxies we know are just one branch among thousands we've yet to discover. It's possible that our surveys have been biased from the beginning, drawn to the bright, the nearby, the structured. And that only now, with telescopes like JWST, are we starting to see the real picture. A universe filled with galaxies that grow in different ways, under different rules, from different starting points. And if that's true, then maybe the strangest thing about these early galaxies isn't how unusual they are. Maybe the strangest thing is that we ever thought they were unusual at all. There are moments in science when a single discovery reshapes an entire field. It doesn't happen often. Usually, progress is gradual, an accumulation of evidence, a slow refinement of ideas. But once in a while, something appears that is so unexpected, so unexplainable, that it forces everything else to be reconsidered. This galaxy, the one that looked too massive, too bright, too old, and too alive, might be one of those discoveries. It began as a curiosity, a puzzling data point at the edge of what we could see. But as more like it appeared, it became clear that it was pointing to something larger, a fracture in the foundation of our understanding. It wasn't just one galaxy that defied the rules. It was a whole population. And the rules, it seemed, were no longer holding. Already, this discovery has inspired dozens of new models. It's driven debates in cosmology conferences. It's rekindled discussions about quantum gravity, early universe dynamics, and the possible evolution of physical laws. Some scientists are cautious. Others are excited. But almost everyone agrees something about this changes the picture. Because the universe is not unfolding as quietly or predictably as we once believed. This galaxy, this anomaly, is not just an object. It's a question. a challenge to the neatness of our theories, a whisper from the early cosmos that there is more to learn, more to unearth, more to reimagine. It reminds us that the universe is not a solved puzzle. It's a living mystery, vast and wild and full of surprises. And as our telescopes sharpen and our models evolve, we will return to this galaxy again and again, not just to understand it, but to understand what it's trying to show us. Because in that quiet, glowing smudge of starlight, the entire story of cosmology might be preparing to turn a page. And now, as your eyes grow heavier and the universe begins to fade softly into the background, let's drift together into the quiet. The galaxies are still out there, all of them, spinning, colliding, shining, whispering their stories through starlight that takes billions of years to reach us. That light travels farther than we can imagine, across the growing fabric of space, just to end up here, falling gently into the lens of a telescope, or into your mind as you listen in the dark. And among those galaxies, out at the very edge of the visible universe, sits one that shouldn't exist. Quiet, massive, impossible. A galaxy that formed too early, grew too fast, lived too brightly. A galaxy that challenges what we thought we knew about how matter assembles, how time unfolds, how space evolves. It sits there like a question mark, glowing with the light of a billion stars, stars that shouldn't have had time to form. And yet, they did. The universe is full of these gentle contradictions, soft impossibilities that hum beneath the surface of everything we observe. They remind us that we're still beginners in a cosmos far older and more complex than we can yet comprehend. And that's part of the wonder. Every discovery leads to more questions. Every answer opens a new door. Every galaxy, even the quiet ones, carries the weight of ancient light, stories told across incomprehensible spans of time, now arriving softly, like lullabies, to guide us into sleep. So let yourself drift now, out past the spiral arms, beyond the local group, farther than even time can follow. Let the stars blur into fog, the galaxies into whispers, the whole cosmos into a gentle rhythm behind your breath. You're floating now, not falling, not rising, just held, like light between stars. And if you happen to still be awake, you can go ahead and watch the next chapter now. But if not, just rest here among the galaxies and sleep